So unit 4 is about density curves and normal distributions. Following is a histogram of test scores of 5,000 students taking a standardized grade 3 math test. So first of all, what is a histogram? We have already learned about histogram in our unit number 1. Histogram is basically a figure in which we have our data sets on the x-axis and frequency on the y-axis. So grade 3 students take the math test, and about the audit, how many students score. The score is represented by an histogram. The all bars represented what are the scores of the students. So this is a histogram that represents the students of maths taking math test, and there are total 5,000 students. So what is the density curve? Scores of many students on this test have a rather regular distribution. The distribution is symmetric with a fairly smooth pattern descending from the center on each side. There are no gaps or outliers. So we have already learned what is symmetric. What is the word meaning symmetric? Symmetric means that distribution is equal from both left side and right side. We also learned there is some word called left symmetric, symmetric to the left, and symmetric to the right. Symmetric to right. So what is symmetric to right? That all of the data is concentrated on the left side of the figure, or all of the data is concentrated on right side of the figure. And symmetric means the data is not concentrated either on left or right side, but it is on the center of the figure and it is in the middle of the figure. So this is symmetric. Okay. Now there is a word called no gaps or outliers. What is the meaning of outlier? If I have a math test, 5,000 students have given math test, and all of the students have scored, the total marks are 100. All of the students scored around 50 marks, from 40 to 50 to 60. So 42, 44, 67. These are the marks scored by most of the students. So this by almost all of the students. So this is called it no outliers. But if such thing happens that two of the students scored 100 marks, so these two students are called outliers because they are outlying by the regular data. Or if this happens that three of the students failed the test and scored 2 marks, 3 marks, 4 marks. So 2, 3, and 4 is an outlier. So what is an outlier of the data? That whatever the data is, what is the main concentration of the data? There are few elements that are very less or very large. So the elements that are very less or very large are called outliers. Got it? So we have learned about two words, metric and outliers. Now next is, we can fit a smooth curve through the tops of bars in the histogram to get a good description of the distribution. So how to make a curve? This is very easy. About the center of all the bars, we plot a point. In the middle of the bars, we plot a point, and then we match all the points, and that make a curve. Density curve. We call this curve a mathematical model for the distribution. It is an idealized description of the data and offers an overall picture of the distribution without considering small irregularities or outliers. In general, a smooth curve is easier to work with than a histogram. The picture we get from a histogram depends strongly on the number of classes and interval lengths we choose. This is not so when using a smooth curve. There are no intervals. Our eyes respond to the area of the bars in a histogram. A histogram can be selected to have a total area equal to 1. So that area of the bars represented relative frequencies or proportions of observing falling within that class. So you have to take class intervals and the lengths. So obviously if we have 5,000 students, so we'll take the students who are get the marks from 10 to 20, from 20 to 30. We take class intervals to draw the histogram. So according to the class interval, the shape of the histogram varies. Now the total area is taken as 10. So in the frequency is over here. So this is a histogram formed. But if total area is taken as 1, so this is a histogram formed. So what is then? Suppose we are interested in the proportion of students with scores less than 60. This represents 1600 students, or a proportion of 1600 over 5,000, 0.32 students. So obviously, if we are interested in the students less than 60, so this is 60. So all of these students are less than 60. And this is about 1600 students, or 1600 over 5,000 students. What if we look at the area of the left of 60 underneath the curve? Just we did with the histogram, we can scale the area underneath the curve so that it is equal to 1. Now, the areas underneath the curve represent the proportion of observations falling within the range of interest. The proportion of values in the interval is equal to area of interval total area of under the curve, which is equal to 1. Proportion of values in interval is equal to area of the interval. So all of the proportion of values in this area will be equal to, when we will sum all of the values of the proportion in this area, this will be equal to total area under the curve. Density curve. The area shaded under the curve is equal to 0.3192. We will learn how to find these areas shortly. Note that the proportion we estimate using the area under the curve is 0.0008 away from the true proportion. The curve describing the overall shape of a distribution is called density curve. So what is density curve? The curve that describes, this is the curve that describes the shape of the distribution. That curve which describes the shape of the distribution is called density curve. All density curves have following two properties. The curve lies strictly on the above x-axis. The total area underneath the curve and above the x-axis is equal to 1. So density curve cannot be like this. It cannot be like this. This is wrong. Density curves are always above the x-axis. One thing, the total area of the density curve will always be equal to 1. So these are the two properties of density curves. Okay. The area under the curve and above the x-axis covering any interval responds the proportion of all values falling within that interval. The previous example illustrates that the area under a density curve offers a very good approximation to the areas of the corresponding intervals in the histogram. Now, suppose we have a theoretically infinite population, very large population. For example, suppose we were to construct a histogram representing the heights of all male Canadians or GPAs of all U of M students. So if we have a very large data, what will happen? If the proportion is infinitely means sufficiently large. So we can construct a histogram with as many intervals as we want. Suppose we construct a histogram repeatedly reducing the length of each interval so that the number of intervals gets very large. The representation is essentially a density curve. So what is a density curve? When there is a very large data and we represent very large data with a histogram, and that histogram basically represents a curve, that curve is known as density curve. So for example, this is the case that this is basically a histogram. This is also a histogram, but the intervals have been smaller now. This is more smaller and this is very smaller. So as soon as the letter becomes larger, the density curve becomes more smooth. In this case, the density curve isn't that smooth, but in this case, the density curve is more smooth. So as soon as the data will increase, if the data is sufficiently large, if it's infinite data, then the density curve will become more smooth. The graphical tools we have used thus far are applicable to sample or finite populations. Density curve describe the distributions of continuous variables for infinite populations. Density curve describe the distributions of continuous variables or for infinite populations. Infinite populations, the populations that are very large. Continuous variables, the variables that keep on continuous. We have already learned about continuous variables that keep on continuing, that does not stop, that are not specific. The distribution shown below for some variable x is known as a uniform distribution. So what is a uniform distribution? That is uniform or symmetric, that is not like moving towards one side or another side. The area underneath the curve is equal to, area is equal to base into height. So what is the base? Base is 4 minus 0 and height is 0.25. So the area under the curve is base into height. So what is the base? Base is 4 minus 0 and height is 0.25. So we will solve this and we will get the
90.
Okay, so we can find the proportion of values of x falling in the given interval because every interval is just another example. Suppose we are interested in the proportion of values of x falling between 1.6 and 3.3. So now this proportion is equal to x greater than 1.6 less than 3.3. So we are interested in the values between 1.6 and 3.3. So between these two intervals, x should be, because this is x, this is horizontal axis, x should be greater than 1.6 and less than 3.3. So it will be equal to 3.3 because it's base multiplied by height. So what is the base? 3.3 minus 1.6, and what is the height? 0.25. So this is the proportion of the values. The distribution shown below for some variable x is known as triangular distribution. What must be the value of the maximum height h in order for this to be valid density curve? The area of the triangle is calculated as 0.5 base into height. So we know one thing, that area of rectangle is equal to base multiplied by height. But area of triangle is equal to 1/2 base times height. Why this happens? Because this is rectangle, and when we divide it into two halves, we get the triangles. It's 1 and 2 triangles. So because when we divide the rectangle into two halves, we get one triangle. Therefore, triangle area should be divided by 2. So area of triangle is 0.5 base into height. So this would be 0.5 into 0.5 into h is equal to 1. So for this case, they're saying that what must be the value of the maximum height h in order for this value density curve. So we know that the area of the density curve should be 1. Area is equal to 1/2 base into height. So it's going to be 1/2. What should be the base?
5.
5. And what should be the height? We don't know, but we know the area is always equal to 1. So 2 will go there. It will be 2 is equal to 5 into 8. So it would be 2 divided by 5 is equal to 8. So it would be equal to 0.4, which is equal to 8. The median of the distribution is described by a particular density curve is the point on the x-axis with area 0.5 under the curve to each side. The mean of the continuous distribution is the balance point along the x-axis. This is the point at which the distribution would exactly balance if it were made of some solid material. So median is the point of the distribution curve where the area is 0.5 under the curve. Basically, it is the middle point. But mean is the point where it balances itself along the x-axis. Let's take it. Population distributions can also be described by their shapes, symmetric and skewness. The mean and median for a symmetric distribution are equal. For a skewed distribution, the mean is closer to the tail. So we have already learned this thing that if we have a symmetric distribution like this, mean is equal to median for the symmetric distribution. But if we have distribution like this, like it is skewed to the left, then for a distribution that is skewed, the mean is closer to the tail. So median will remain in the center. Median is there in the center, but mean is closer to the tail. If the distribution is like this, then median is still in the center, but mean is in the near to the tail. So this is all about the density curves, mean, median, and mod. Mean and medians. The standard deviation of a continuous distribution is mathematically more complicated. So we already have learned what is standard deviation in our last unit. But unlike the mean's conceptual definition as the balance point, there is no such intuitive description for the standard deviation. The variance of a continuous distribution is the average square deviation of an observation to the mean of the distribution. We must distinguish between the sample mean x bar and population mean, which we denote by mu. The population mean is the average value of some variable for all units in the entire population. Similarly, while S is the sample standard deviation, we denote the population standard deviation as sigma square. So now there is one thing that we have learned about mean. We do not mean by x bar, which is equal to summation x over n. So now what is the difference that if we have a population and we have a sample? So these are two different things. What is population? Population is the entire thing. That is the thing of all units. Sample is a small unit taken from the population. So for the sample, we do not mean by x bar, but for the population, we do not mean by mu. So if we say mu, it's the population mean. If we say x bar, it's the sample mean. Similarly, if we say standard deviation, about standard deviation, if we say sigma, it's going to be population variance. And if it S, then it's standard deviation, simple sample standard deviation. So S is going to be for sample standard deviation or sample variance. And sigma is going to be for population standard deviation or population variance. So there are different alphabets or different denotions for population and sample. This need to be remembered because it can come in the question. So we call such values as mu and sigma parameters of the population. A parameter is a number that describes the entire population. So these two symbols are called parameters. What is the parameter of population? What are the parameters of population? Mu and sigma. What is the function of mu? This is the mean of the population. Sigma, this is the standard deviation of the population. Because we are dealing with very large populations, the values of parameters are usually unknown. For this reason, we use statistics or estimators such as X bar or S to estimate the values of parameters. A statistic is a number computed from sample data. Now there is a difference between statistic. What is statistic? This is a number that we get from sample. Statistics or estimators. Remember this thing. Statistics or estimators are something that we get from sample. Parameter is something that we get from population. These are the two words that should be remembered. Mu and sigma goes for population, X bar and S goes for sample. So this is important thing. Normal distribution. The density curve we looked at previously is called a normal distribution curve. So this is the normal distribution curve. Normal distribution. Normal distributions arise naturally for many different variables: height, test scores, diameters, betting averages, lengths of pregnancies. Normal distribution, the parameter mu, which can take any value, positive or negative, sigma, which must be non-negative. Now remember this thing. What is parameter? That comes from population. There are two parameters of population, mu and sigma. What is mu? Mu takes any value, can be either positive value or negative value. What is sigma? Sigma must be non-negative. Non-negative means it must be positive, it cannot be negative. Okay. It's completely characterized normal distribution. That is, they tell us everything we need to know about the exact form of distribution. The set of all normal distributions, that is for every combination of mu and sigma, there are infinitely many of them, is called the family of normal distribution. Zilla, give me 1 minute.
Okay.
Okay, so you get to know about the mu and sigma. Mu is always mu can be positive or negative, but sigma is always non-negative. Okay, so the important point was the set of all normal distributions, that is for every combination of mu and sigma, is called the family of normal distributions. There are infinitely many of them. There are not only two of them, mu and sigma, but what we have learned are two parameters, that is mu and sigma, and they are family of normal distributions. So if someone asks you what is a family of normal distributions, family of normal distributions. So it is mu and sigma. What is mu? This is the mean of the population. Sigma, this is the standard deviation of population, not sample. So these are two important points. Okay. Normal distribution. Some characteristics of a normal distribution. Bell-shaped, single-peaked, symmetric about its mean. So there are three properties: that it is like a bell shape, like this. It has a single peak, and it is symmetric about mean. So if it is like this, like there are two peaks, it means it is not a normal distribution. If it is not bell shaped, it is like this, a straight or something else, it means it's not a normal distribution. If it's not symmetric about mean, it means it's not a normal distribution. So if you get any curve like this, and if someone asks you, is it a normal distribution or not, you have to check 3 points. One is, it should be bell shaped, it should be single peaked, and it should be symmetric about the mean. Not that the curve never actually touches the x-axis, but the height of the curve becomes infinitely small as the value of the variable x get extremely large or small.
Symmetric about its mean means like it shouldn't be left.
No, shouldn't be left or right, yes. Like this. Shouldn't be symmetric left or shouldn't be right.
Okay.
Okay. So consider the two normal distributions shown below. Both distributions are normal with equal means mu, but unequal standard deviation sigma 1 is greater than sigma 2. So in this case, because it should be symmetric about mean, so this is the mean and this is the mean. So they both are symmetric about mean, but this is the thinner one and this is not the thinner one. So what is the difference between them? This sigma. Sigma, that is called standard deviation, is different, but the means are same. The two normal distributions are shown below have equal standard deviations but unequal means. So what is this happening here? They're saying have equal standard deviations. So the standard deviations means the width. This width is called, basically represents the standard deviation. So standard deviations are equal, but its mean is over here, its mean is over here. So mu is greater than mean 1. So it means the means are not equal, but standard deviations are equal in this case. Okay, if a variable x has a normal distribution with mean mu and standard deviation sigma, we write. So we have a variable x and we say that the variable x has mean mu and sigma this. And it has a normal distribution. So normal distribution stands for n. N, mu, sigma, and we like it. So if it is written like this, sigma, n, mu, sigma. So it means that this is the normal distribution for mu and sigma. Symbol, this indicates that the variable x follows a normal distribution. So variable x follows a normal distribution. So n stands for normal distribution. Despite the different means and standard deviations, all normal distributions have the following rule in common. Approximately 68% of all values fall within one standard deviation of the mean, mu plus minus sigma. 95% of all values fall within two standard deviations of the mean, mu plus minus 2 sigma. 99.7% of values fall within three standard deviations of the mean, mu plus minus 3 sigma. This is called 68, 95, 99 rule. 99.7 rule. So what is this rule? That most of the values are falling over here 99%, then 95%, and here 68%. So this says that most of the values fall here 99%, 95% over here, and 68% over here. So what is this happening? That in center, this is mu, that is mean. So if we will add a sigma over here, we will get the values over here. If we will add 2 sigmas, we'll get the values over here. If we will add 3 sigmas, we get values over here. If we subtract sigma, we get here. If we subtract 2 sigma, we get here. If we subtract 3 sigma, we get here. So mu plus minus 3 sigma almost covers all the values, almost cover 97%, 97% is 99%. So mu plus minus 3 sigma, like plus means covering on the right side, minus means covering on the left side. So mu plus minus 3 sigma on the right and left side almost covers 99% of the values of the data. So if we can determine how many standard deviations an observation is away from its mean, we can determine the approximate area under the curve corresponding to a certain interval. If we know that x and mu, x is okay for normal distribution and we have an observation x, then how many standard deviations is x away from mu? So now we have to find out this. This is very special number of the family of normal distribution. The distribution is special because if it has a mean of mu is equal to 0 and standard deviation of sigma is equal to 1. We call this standard normal distribution and denote it by z, the variable which is it represents. So what is z? If I have a normal distribution and in my normal distribution, I have mean 0 and sigma 1, then that normal distribution is called standard normal distribution and that standard normal distribution is denoted by z. So z is equal to standard normal distribution in which mu is equal to 0 and sigma is equal to 1. So normal distribution with mu 0, sigma 1 is called standard normal distribution denoted by z. In fact, we can transform any normal variable to have this distribution. This is very helpful because the standard normal distribution is much more easier to work with. Obviously, because standard normal distribution has mu 0, mean 0, and standard deviation 1. So this is very easier to work with other than normal distributions. Normal distribution. To transform a normal variable x into a standard normal variable z, we find the z-score, also called the standardized value of x. For a given observed value of x, the z-score is calculated at z is equal to, now how to find z? Z is x. What is x? All the observations. 1, 2, 3, 4, all of the observations. Z is equal to x minus mu, this mean of the population, by sigma, standard deviation of the population. This helps us to calculate z. What is z? Standard normal distribution. The numerator tells us how far x is away from mu, and denominator scales the value to be in standard deviation units. And also, so z is in fact the number of standard deviations and observations x in the form of mean mu. Suppose it is known that the heights x of adult male Canadians follow a normal distribution with mean 178 centimeter and standard deviation 6 centimeter. So obviously we are given mu, which is equal to 178 centimeter. The data is given here. Sigma, which is equal to 6 centimeters. So it is following a normal distribution. It means they are saying that it is following a normal distribution. So it is 178, 6, mu and sigma. Now, we measure one man's height to be 187 centimeter. The z-score of this man's height is, now one man's height is 187 means this is the value of x. Now z is equal to x minus mu over sigma. What is x? 187 minus mu is 178 by x is 6. So the answer would be 1.5. So this is how we calculate x. To find x, we must be given x. In other words, this man's height is 1.5 standard deviations above the population mean. One point five standard deviations above the population mean. So about the population means it is greater than the population mean. How much greater? 1.5. So this Z is telling us this thing. Find the appropriate proportion under the standard normal curve. Note, when finding proportions for any distribution, it is always helpful to sketch the distribution and shade in the area of interest. This will help you visualize the problem to ensure you know what area you are looking for. Now, P, Z minus 1 to 1. Answer. By definition of our rule, the approximate proportion of observations falling within one standard deviation of the mu is equal to 0 and z is minus 1 to 1 is 0.68. So now this is when it comes by definition of our rule, it means it is the rule. So approximate observations, they are saying whenever z is from -1 to 1, the normal standard deviation is 0.68. So this is almost the rule. When z is between 0 and 3, it is when z is -3 to 3, it's 0.997. So the symmetry of the normal distribution, we know when z is 0 to 3, it's 0.997 divided by 2, because when it is from -3 to 3, it is 0.997. And when it is 0 to 3, so it is half. So if it is half, we have to divide by 2 and we will get 0.485. So when z is greater than 2, so when z is greater than 2, we know z is -2 to 2, it is 0.95. So when it is greater than 2, it means P of z is less than equal to -2 plus P of z is greater than 2 is equal to 1 minus 0.95, 0.05. So P of z is greater than 2, 0.05 divided by 2 is 0.025. Now z is between -2 and 1. We divide this proportion into two areas and we get -2 to 1 is equal to -2 to 0 and then 0 to 1. So we have to calculate for -2 to 1, this whole area. So we will divide -2 to 0 and then 0 to 1. So for -2 to 0, we already know it is 0.95 divided by 2. And for 0 to 1, we already know 0.6 divided by 2. So we will get 0.815. We can handle such problems for any normal variable x and mu sigma using the 68, 95, 99.7 rule by first standardizing the value of x to find the interval of interest in terms of z. The standard normal distribution will serve as a frame of reference which we will use to find all of our proportions for any normal variable. Since z is defined as the number of standard deviations, an observation is away from its mean, and this is exactly what the rule applies to. Consider again the normal distribution for male heights, n 178 and 6. What proportion of Canadian adult males are between 166 and 190 centimeters tall? So now for 166 and 190. Now we have to find for 166 and 190. So z is equal to x minus mu over sigma. So now this is x, 166. 166 minus what is mu? 178 divided by sigma. What is sigma? 6. So you will get, what we will get for this? 166 minus 178 by 6.
-2.
Minus 2. Okay. Now the second value of x is 190. So we have z is equal to x minus mu over sigma. So what is x? 190 minus mu is 178 by sigma is 6. So what you will get?
2.
2. So now we have P of -2 less than z less than 2, because for the value of x 166 we get -2 and for value 190 we get 2. So we get this thing. Now what is the value equal to -2 and 2? Because we learned a few values by definition. Where is the value for -2 and 2?
There's a table that he provided us.
Yes, a table is also provided, and from the table we can also find out the values. But a few values we may learn that are given by definition. But actually there is a Z table provided, and that Z table will give you the value of 0.95. Till here, it is the calculation part, then by table you can get the value 0.95. We do have Z calculators and Z tables. Okay. So this is the graph. Okay. Note that we standardize the values of x by subtracting u from x and then dividing that quantity by sigma. We have transformed the variable x into the standard normal variable z. And so the problem is now rephrased in terms of the standard normal distribution. Note that we did exactly the same thing to all quantities inside the bracket to maintain the inequality. What proportion of Canadian adult males are between 178 and 196 centimeters tall? So for this thing, again, what we're going to do is for 178 would be our x. So again, it was z is equal to x minus mu over sigma. So what is x? 178 minus 178, because mu was also 178 by 6. So it would be 0. And for the next one, it would be 196 minus 178 divided by 6, which will be equal to 3. So between 0 and 3, the table can give you the value 0.4985. Standardization. Okay. Note that for any continuous variable x, the proportion p of x less than equal to x is exactly equal to the proportion p of x is less than x. So if it is y, the proportion x less than equal to x is equal to the proportion x less than x plus the proportion x is equal to x. But this later proportion is 0 as it corresponds to the area of a line. So for continuous distribution, it does not matter if you are looking for this or this. So if in case you are looking for p of x is less than equal to x, for continuous distribution, it is equal to p of x is less than equal to x. So this may come in the multiple choice questions, that for continuous distribution, less than equal to and less is equal to are both same things. They are not different things. We are now ready to be able to find any proportion corresponding to any interval for any normal distribution. Table 2 gives us a proportion under the standard normal distribution to left of any value z. Table 2 consists of two pages, one for negative values of z and one for positive values. The numbers on the column under the z at the left side of the page represents the units and the first decimal place, while the values in the row of the right of z represents the second decimal place. The value at the intersection of each row and column is the corresponding proportion to the left value of z. For example, the entry of the at the intersection of 1.8 and 0.02 is 0.9656. This represents the exact proportion under the standard normal curve to the left of the value of z. The table entries are listed only for values of z between minus 3.49 and 3.49. This is because very close to 100% of the area under the standard normal curve falls within the interval. As such, we can take the proportions less than minus 3.49 or greater than 3.49 to be 0. For example, z greater than 5.17. Okay, so they are saying the table representing the values between this and this. So if the values is greater than 3.49, for example, 5.17, it is 0. For example, less than minus 3.49, minus 3.85, it is 0. And minus 6.22, it is 1. 4.7, less than 4.73, it is 1. So this is according to the table. Find the proportion under the standard normal distribution, normal curve corresponding to the following intervals. So now we have to find the proportion for p of z